Hi, I'm Sonal. This is my dissertation. And so I would be talking about distantly supervised information extraction using bootstrap patterns. So let's assume you're a busy researcher researching substance abuse problems, and you come to know of this forum, medhelp.org, in which people come and talk about the substance abuse problems. So something like estranged husband was on huge amounts of opiates, 80 perks a day, and plus oxys and morphine and Valium and so on. And all you know from the previous work that people have done in bioinformatics is this annotator called NCBO annotator, which extracts, people have written down, spent their PhDs writing this ontology of drug names and symptoms and conditions and stuff, and that it can only extract 3 of them because that's the exact match it does. So you only extract opiates, morphine, and Valium. But what about all other morphological variations and new drugs that people keep trying all the time that are not in the dictionary? And problems like this are pretty relevant in real world because you are some researcher in your own domain and you want to extract entities of some particular type that no one else has done work on or hasn't labeled any data from. And you don't want to sit down and label thousands of examples. All you want to do is start with some starting point and then generalize from there. So another example, so over here, you want to extract these things that are not extracted by the NCBO extractor. Another example is if suppose you are from Yelp and you're extracting food items. So if the sentence is like, we ordered the empanadas for an appetizer, and then it comes with 3 different sauces. My wife ordered the, pardon my pronunciation, arroz con pollo, and I had lomo saltado, and we split our order of mac and cheese. Mostly you would know that empanadas and mac and cheese are food items, but you also want to learn all these new food items or fusion items that people haven't yet written down as food stuff. And most of the work that has been done in last decade of machine learning and NLP is on supervised models. So you have large amounts of labeled data, and you want to create this really nice kernel function on something, or you want to improve this conditional random field model or sequence models. But the common problems with that kind of work is that in most of the common things that people work on industry or want to extract information from, there is no supervised data. It's harder to do domain adaptation or improve the extractor for different vertical. And sequence models like CRFs, they are very successful at entity extraction. If you want to just extract names and locations and organizations, they're really good at that. And the reason is because they're context aware. They look at the things on the left, things on the right, and they can use a lot of features. But they also require large amounts of labeled data. And it's hard to calibrate them. So you can't just say that I want to extract only high precision extractions. It's harder to have thresholds on CRFs, for example. And the other potential system is just handwritten lexicons that people in different non-CS world actually do it. They spend their PhDs writing these ontologies and lexicons, which have a poor recall because language changes all the time. And it's impractical and expensive. So the idea of the project is starting with few entity types that you want to learn entities of, and a few examples of each type. So over here, if you want to learn diseases and treatments, and the only thing you know is, for example, asthma attack, diabetes, and pain are diseases, and ibuprofen surgery and pain medications are treatments, and you have huge amount of unlabeled text, then can you learn entities of more entities of the same types? And feel free to interrupt me if you have any questions or comments.
Since you mentioned that, can you just go back to the comment about CRFs? Mm-hmm. And can you just explain why they're hard to calibrate?
So over there, suppose if you want to say that my threshold, if you want to see, put a threshold on the probabilities, it's hard to get a probability of a word. So because it's harder, it's easier to do in certain models, certain sequence models, but especially in CRFs because it's building the whole sequence for putting a particular probability on this word extraction. It's harder.
Couldn't you just train a confidence model separate from the CRF?
Right. So you can do like things on top of it to build to see more do things, but like not. It's harder to do in the basic model. But if you suppose have logistic regression, for example, it's much easier to do things in which you just say the threshold. My threshold is 0.8, and then you just extract those things. but it gets harder in sequence models. Okay. So you want to do distantly supervised entity extraction, and also hopefully you also want to do the distantly supervised relation extraction. So over here, if suppose the relations are state in which person is born in, and the only thing you know is that Obama was born in Hawaii, and George W. Bush was born in Connecticut, or if you have relations like work for, so Obama works for US, and someone works for General Motors, and then you have lots of unlabeled text, and you want to extract more pairs of the same type that are in the same relation. And most of the times, you don't even have to write down these examples. You can get those extractions that people have already worked on. So for example, Wikipedia info boxes, they're really useful to get labeled information about relations. And there's been a lot of work done, for example, knowledge-based population tasks, to use these info boxes to start with and learn examples of the same type. And then you can also use web pages that people have created. They have made tables of list of food items, for example, and you can start with that. And that would be a seed thing. So the goal of the project is to build practical information extraction system that require only a few examples. However, in real world, quantitative performance is not the only criteria. People do not trust black boxes. So I was attending a talk by Maya Gupta at Google, and she was saying that when she went to Google, and she was amazed at how many product groups do not use machine learning, even though Google has so many machine learning groups. And the reason is that people just do not trust them. People do not understand what's going on inside them, and they don't want to deal with it. They have their own handwritten rule-based systems, and they want to just build on top of it. So you want something which is interpretable. You can look at an error and see why is this error coming from and how you can improve it. So things that can help you do error analysis better and maybe then improve the system better. So the new goal is build practical and interpretable information extraction systems that require only a few labeled examples. And so here's just a peek into the system result that I built. So suppose you want to extract food items from Yelp reviews. And I was just playing around with the system. So I took some 2,000 reviews. In a minute, I looked at the few reviews and wrote down a list of 4 items. So over here, crab salad, craft beer, eggs, chowder, and horseradish. And then I just used the system with no tuning and ran the system, and I got more entities of the similar type. So you can extract entities that are food items. There's obviously some false positive, but the list looks pretty good. So here is a brief outline of the talk. We'll go a bit into the background and patterns which I use for the system, and a bit about Bootstrapped Pattern Learning, which is the architecture of the system. And I'll talk about that this Bootstrapped Pattern Learning is pretty effective, and I'll talk about 2 new tasks. One is to extract key aspects out of scientific articles, which might be of interest to some of you guys working on scholarly project. And then the second part is extracting information from online medical forums. And I'll talk about improvements in the next part of the talk, which is how to improve pattern scoring in this Bootstrap Pattern Learning and how to improve the entity scoring. So let's see what are patterns. Patterns are not new. They have been around for a very long time. People use them all the time. These are feature templates. So for example, if you have a surface word pattern like I live in X, which is a noun, so this is the target entity you want to extract, comma, a word which is a state. This would match a sentence, I live in Stanford, comma, California, and you will extract Stanford as an entity. Another pattern can be a parse tree pattern. So this is a dependency parts of a sentence. And you have a trigger word, which is work. And you have some dependency, so preposition on. And you want to extract the phrase tree that matches this pattern. So here you will extracting information because it matches works on over there. And why do we want to use them? Because they are really successful in industry. They're pretty effective, and they're interpretable. So some people from IBM folks, IBM, they did research into what people use in industry. So 70% of big industrial systems that do entity extraction use patterns or rules of some type. And though most of them are handwritten rules, because that's what it's easy for them to do, they're not trained to be machine learning people. And it's because they can just look at them and then cope with errors. They can add a new rule to the system, which will remove the error that they're experiencing right now, and it's easy for them to do it. And they can identify the sources of errors by inspecting the output. And it is a part of hybrid systems that you might have heard of, like never-ending learning system from CMU, Know-It-All, Reverb, Ollie. I'm pretty sure a lot of you guys are familiar with that. And it's part of all the hybrid systems. So if you improve the pattern learning systems, you would probably improve the hybrid systems too. So I'll go into what exactly is this Bootstrap pattern learning architecture. And here, I'll go into each component one by one. And it's an iterative procedure. And you start with some seed set of entities. So it was introduced by Thelen and Ryloff in 2002. And what you do is that you start with the seed set of information that you already have. And you label the data using this current information. So for example, if you want to learn animal entities, and all you know is dog is an animal, and you have some text. So text is, I own a dog, Tommy. I run with my pet dog and nap with my pet cat. I also own a house. Then you label both the instances of dog in this text. In the next component, you create patterns around this. And in this example, I'm working with surface word patterns. So I'm just looking at the words and the type of words in the left window and the right window. But you can also work with dependency patterns and other kinds. So here, there would be a lot of candidate patterns. But I'm just going to talk about 2 of them. So for example, 2 of the candidate patterns would be my dog X and my pet X, and which we extracted because we labeled the 2 instances of dog over there. Just a note on pattern generation. For example, if the sentence is, President Barack Obama has a dog named Bo, and you want to create patterns around the word dog, then you can also look at other properties of the words nearby, not just the word itself. So you can look at the president is a, NER is a title, and the named entity tag of Barack Obama's name, and then maybe the part of speech tag of is determiner, and so on. So the patterns are actually, you can create how many ever you want, and in many different ways. Similarly, you can have another pattern like X named something which is a name, which would match dog named Bo. And something like has X named. So you can ignore stop words like and so on. So you generate all possible patterns around the labeled entities. And you can look at parameters like maximum and minimum window on each side of the entity, the part of speech tags, the NER tags, and the parse tree tag restrictions and stop words. If you're working with dependency patterns, then you can also look at the trigger words, the head, the parents, and the ancestors of a current word. And you can look at the depth into which you want to go in a dependency tree. And some kind of dependency, so you can have restrictions on what dependencies you want to extract. So once you have the candidate patterns, and there should be a way to score these candidate patterns, that this is a good context to extract, and this would extract good entities. So over here, each pattern is scored according to the entities it extracts. So owner X would extract 2 entities. One is a dog and a house. So dog is positive. We don't know the label of the house. And it gives you a score S1. And in my pet X, the same way, it extracts 1 positive entity dog. And it extracts 1 unlabeled entity cat. And maybe the scoring function gives it a score S2. So each pattern is scored by the number of positive, negative, and unlabeled entities it extracts. So one commonly used scoring measure is R log F, which basically just looks at the ratio of the positive to all the entities that the pattern is extracting, and multiplied by log of the number of positive. And the reason of log is that it will give higher weights to scores to patterns that are extracting more positive entities. So once you score these candidate patterns, you choose the top ones, and you apply them back to text. So what I mean by that is that let's assume you have a good scoring function. So it gives the second pattern higher score than the first pattern, because my pet X is better pattern than owner X. And we choose the top 1 pattern, for example. So we'll choose this pattern as one of the good patterns, and we apply them back to text. So we generate a candidate entity cat. So now all the entities that this pattern is extracting is dog and cat. Dog we have already learned. So cat is the candidate entity that you want to see whether it's a good entity or not. So in the last step, you have all these candidate entities that were extracted using all the patterns you have learned till now. And you want to see which of these entities are actually good entities. So you score them using some entity function. So right now, we have only one candidate entity. And let's assume it gives a score, and you learn that cat is another animal entity. A note about entity scoring measures. Different papers use different kind of entity scoring depending on the domain they're working on and what kind of entities they're extracting. What we do is we build one versus all classifiers. So for a particular type of entity, we take all the seed and the learned entities as positive, and examples of all other types as negative. And we also sample the unlabeled entities as negative to improve the negative training set. So for each example is basically one entity, and you extract features from it. So you see what patterns matched this entity, and how many other entities is that pattern matching. Is this entity a common word? Does it occur in Google Ngrams, for example? What is the similarity with other known entities, and so on.
Is there any scope for doing joint learning on different patterns? Like if a word appears in a single sentence as part of a left pattern and a right pattern, maybe that's a higher indication that it's an animal or something.
Right. So right now we are treating each pattern as independent, but definitely that's a good idea.
Is there any way to unlearn? Because if you make a mistake, then you can probably go.
No. I mean, it's not built in yet, but people have done it before, in which from each iteration, they start from scratch. They're like, OK, I throw away all the patterns I've done till now. I'm just looking at learned entities, for example. And then they relearn all the patterns from scratch in each iteration. So there are ways of doing that if you want to just unlearn something. It's harder to do it because it's a generalization system, so harder to know where the error has occurred unless a human comes in and says that this is the wrong feedback. So you do this for t times. And each time you learn some good patterns, and then you learn what are the good entities that are extracted by these patterns, and you keep learning. So the two most important components of this is how do you score patterns and how do you score entities. I'll talk about two new applications that we worked on and show that Bootstrapped Pattern Learning is pretty effective for it.
Can I just ask a question before you get into the applications? If you just go back to the previous slide. So when you iterate, right, people generally report, right, that there's semantic drift where, right, because the data is getting somewhat more uncertain, and so the patterns in iteration T are not usually as good as iteration 1. Did you find that? And if so, did you deal with that in some way?
Yeah, semantic drift is a real problem in Bootstrap systems. Unfortunately, I didn't have time to work on it, but it's a very interesting open-ended problem. How do you detect semantic drift, and how do you see how far they are going off from the seed set? The question is, how do you even detect how far is good, and do you want to generalize that far or not? I think it's a very open-ended and really interesting research problem.
So you just chose a fixed T and
yeah. I'll talk a bit about evaluation, in which I have a hand-labeled list of test set in which I stop learning a system if the precision drops below 75% on that test set. So you stop at some point knowing the precision. So I'll talk about two applications. So the first one is you extract key aspects from research papers. And the second one is extracting medical entities from online health forums. And I'll go into the first one. And so these are sentences from research papers. So they are pretty grammatical sentences. However, the entity is ambiguous. And I'll talk about why the entity is ambiguous in these key aspects. And because we have grammatical sentences, we work with dependency patterns. And I'll get to that. So the goal of the project is, given a paper's abstract, you want to extract what is the main contribution of the paper. what are the techniques they're using, and what domain they're applying to. And this works well for dealing with NLP papers, for example. It's a very applied field, so you have some techniques you're using, and you're actually working on some particular domain. So over here, for the example, the abstract is we propose a new framework for parsing Twitter messages. Our system uses this other Twitter POS tagging system that someone else has built. So the focus of the paper is parsing Twitter messages. The technique they're using is they're using some other part of speech tagging system to do their stuff. So that is one of the techniques they're using. And the domain is, again, parsing Twitter messages. So over here, for example, part of speech tagging is being used as a technique. But for some other papers, that was a domain. They were actually improving part of speech tagging. But depending on the context, that this paper actually uses it as a technique to do parsing. So we use dependency patterns. What we do is we handwrite the few initial patterns. So we say, in the first iteration, we write what are the good patterns for extracting focus, domain, and technique. So for example, over here, one of the focus patterns would be propose something, which is a direct object. So that is something, a main contribution of the paper. Or a technique with using something. So using a direct object, you're using a technique to do something. And you learn new patterns by bootstrapping. And here is an example of matching patterns to sentences. The sentence is, we work on extracting information from dependency graphs. This is the tree for that dependency tree for that sentence. And if we are matching the pattern work on, then this phrase tree gets extracted. And we extracting information using dependency graphs as a focus. Similarly, over here, for technique, the pattern is use direct object. That matches as a technique. So we extract dependency graphs as a technique. These are some of the learned patterns using bootstrapping. So for technique, for example, we learn that extracting direct object is a good pattern for extracting techniques. Or model and then some noun that modifies this word model is a good technique they're using. Or domain, it improves something. It is used for something. So why did we even want to extract these key aspects? We wanted to study the influence of subcommunities on each other. So how the knowledge is flowing and how one community is influencing other communities. So we defined the influence as techniques that are borrowed. So one community influences other community if the other one is using techniques that were brought in the community by the first one. For example, speech recognition community brought in HMM, and other people have been using HMM since. So speech recognition community has been pretty influential. Or it produced tools that were used by other people. So part of speech tagging, for example, has been an influential community because other people have been using part of speech tagging to do other things. And we use topic models to assign papers to subcommunities, and then see how from those papers we extract key aspects and see how subcommunities are influencing each other. So here is a graph. So on the y-axis, we have the influence score. And the x-axis are the years from 1981 to 2009. So these are papers from ACL Anthology. And we are looking at subcommunities inside computational linguistics. So the orange one is speech recognition. It has come back into popularity recently, but in 2009, there were very few papers getting published on speech recognition. But still, it has been pretty influential because it brought tools that are used by other communities. The red one, named entity recognition over here, has been increasingly influential because other communities are using NER system to do their things. So some of the most influential phrases out of these two communities is, for speech recognition, there's expectation maximization, hidden Markov. Language, I'm assuming it is like language modeling. And similarly, for machine learning classification, it is support vector machines, ensemble, machine learning, Gaussian mixture. So our system brought these as the most influential phrases of these two communities. So in summary, we studied influence by extracting key aspects using Bootstrapped Pattern Learning. And the only thing we had to do was to write these few patterns starting out and then learn from there. And we defined 3 ways of extracting key aspects: focus, technique, and domain. And we introduced a new definition of influence and studied influence of communities.
The output of your pattern learning algorithm, is that just a list of top patterns, or do they come with associated confidences or probabilities?
Yeah, they're associated with scores. Not necessarily, yeah, those are not really probabilities, but they're scores.
And the second question on the previous graphs, was there a way to validate this, or is this mostly eyeballing and that looks?
Yeah, I asked Chris Manning and Dan Jarofsky to look at it. And Chris mostly, so he just looked at it and he's like, yeah, this makes sense, or this does not make sense, or improve this thing, kind of thing.
So this is Chris Manning eyeball, which is substantially more, yeah.
So then we study the second application, which is you want to extract medical entities from online health forums. And these are people writing when they're sick and other family members are sick, and this is online web forums. So all the sentences are pretty ill-structured. There are many, many spelling errors, abbreviations, morphological variations. So it's harder to do the dependency parsing that we did in the first one. So we learned surface word forms, just the words and type of words in the neighborhood. So the task is we want to extract drugs and treatments and symptoms and diseases from text. So over here, for example, the sentence is, and this is real example from the forum, I plan to start cinnamon and holy basil known to help diabetes in many people. So you want to extract cinnamon and holy basil as drug and treatment and diabetes as a symptom or disease. And people basically come there and talk about home remedies and herbs and whatnot, which you really cannot find in any lexicon. And another example is, my sinus infections were treated electrically with high voltage, million-volt electricity. I did not make this up. This is there, which solved the problem, but the treatment is not FDA approved. So you want to extract high voltage, million-volt electricity drug and treatment. So what we did was we automatically extracted seed sets from web pages and existing ontologies. And we extracted information from 4 health forums, so on asthma, ENT, breast cancer, and diabetes type 2. And we compared with all the other entity extraction systems in which what are the widely used entity extractors in the bioinformatics world, and CRFs and self-trained CRFs, and dictionary-based approaches. So here is the output of the system, top few patterns and few entities from the asthma forum. So on the top are the patterns, on the bottom are the entities. So one of the top pattern is, these are the lemmas of the words. So I, be, put on. So this would match like I am put on. X, which we know, the restriction is there is that the part of speech tag is a noun. Another one is the third one, which is use DT. So this word is basically anything that matches drug and treatment, the existing entities we know. And so it would match something like use ibuprofen and other drugs that you want to extract. And these entities over here are asthma-specific entities, so inhaler, steroid inhaler, and so on, which were not in the dictionaries. For symptoms and conditions, again, on the top are the patterns that get extracted. So something like X followed by something which is symptom and condition, etc. And then on the bottom are the symptoms that get extracted. So lots of spelling mistakes and more modern way of writing things. So this is a comparison between our system and most widely used entity extraction systems in bioinformatics world. On the left, the red are the ones that are false. And you see that MetaMap extracts many worse things than we do. Yeah.
So your system looks like it's doing pretty impressively compared with MetaMap. But so what is it that's giving your system that added power? Mm-hmm.
So MetaMap does a very dumb matching. So it doesn't even look at the context. It does like just dictionary matching.
So you have a more powerful pattern language?
Right, right. So it learns according to this domain, what are the good contexts that are useful. So MetaMap doesn't even look at the domain or the text or whatever. So for example, over here, said matches. So it matches because SAID is an abbreviation of a drug that no one knows about, and people probably do not use on the forums, but still matches because it's in the ontology and the lexicon they have created. So it does a very dumb matching of things. So in our paper, we do remove these things, the very common words, and then see the score of MetaMap and our system still does better because it works on the domain. It doesn't get limited to the lexicon that they produced, and we learn many more new things.
So MetaMap's just looking for particular words in the text.
Right, right, yeah, and they do not learn anything.
Did you try any other pattern learning techniques on this domain?
Yeah, we did. So the existing techniques on these kind of forums and stuff, and we saw that our system performs better.
And why is that?
One of the things is how do you deal with things. So for example, on the domain, you have to do these kind of domain, you have to do fuzzy matching, and you have to know what are the common words. You have to contrast the domain text with general text and so on, which other systems do not take care of, and also just better pattern scoring and entity scoring measures, which are the two most crucial components in the system.
It looks like MetaMap is not using part-of-speech information. How does your system do without part-of-speech information? Is that something?
Interesting question. I did not try that, of not using part-of-speech information.
The grouping drug and treatment, I'm guessing those are grouped together because actually they'd be very hard to distinguish using patterns. And similarly, symptom and condition. What if you wanted to learn symptoms but not conditions?
Yeah, we debated about the classes a lot. And with the current expertise we have in not having any medical background, even defining the classes and how things are. For example, wheelchair, is that a treatment or not? How would you consider that? Is that a different class? So we wanted to just deal with two different classes that we understand and explain what it is. It would be harder, and I think it will require better seed sets to deal with it, in which you can contrast what is a drug versus a treatment. Does that answer your question?
It looks like there's some kind of class engineering involved in making the system work. So definitely, I think lesser number of classes help in any system. The reason was also, we also talked to medical people, like bioinformatics people. I had meetings with them to discuss these things. And according to them, they were not clear what would you consider as treatment. And we're like, well, you have these exceptions. Would this be treatment or that be treatment? And I would say it was more of convenience, and also to see in this very hard domain, which is the patient-generated text. So people in medical domain, they work on doctor's text, which is much easier to parse and do things on. In this patient-generated text, in which people are working on home remedies, they describe the symptoms as heavy heart or a huge brick on my heart and stuff. It's much harder to extract things. So we wanted to just restrict with two classes right now to see how well we can do with these two classes. Even with these two classes, it was a pretty hard task.
So in the medical problem and in the scholarly research papers problem, the pattern is you have a problem and you have a technique, or you have a problem or symptoms and you have a treatment. So in that way, the two are very similar. Well, the difference is in the research problem, the text is a lot more structured and clean compared to online forums. But can you talk more about the difference between the two applications in terms of effectiveness of the pattern bootstrap learning method?
Right. So I think it was, in terms of things that we extract, it was much harder to do entity, well, in some ways harder and easier to do entity scoring in the second one, in which people talk about, so if you have just spelling variations or morphological variations, that's easy to see if it is just edit distance away or similar in some word vector form. But I would say ambiguity was a bigger problem in the first one, in which part of speech tagging, is it the domain or the technique? It was much harder for that as compared to in the second one, in which just figuring out whether this is a good entity or not. It wasn't just drug or treatment versus symptom condition. It was more like, is this even a valid entity to consider? It was a harder problem. And I think like if you can dependency parse your sentences, and if you have time for it, they're much easier to deal with and much cleaner, and they extract better information. The problem is like when you do not have any kind of dependency parses, then you have problems.
Have you done some analysis on the accuracy of your system with regards to different seed sets, different size of seed sets? Because as you go all the way to supervised, you would expect it to defeat your Bootstrap system.
Interesting thing. So I did not include results, but in the first part, I actually compared with fully supervised approaches. And for, I think, domain, we beat the supervised CRF. And the reason I believe is that, well, if you just have more and more labeled data, CRF is just going to perform better. But the labeled data we actually beat the supervised CRF too. I really wanted to work on increasing the seed set size and see what kind of seed sets, not just the size, but the quality of seed set. How do they improve the end system? But I haven't yet worked on it. I want to move forward so I can cover more things. Okay. Some of the numbers in which I'll just point out to the recalls. We improved the recall a lot better than the existing systems. And you can find more baselines in the paper. But the first one is just doing some kind of fuzzy dictionary matching, but also removing common words. So it's not just dictionary. You actually do some kind of intelligent dictionary matching. And it beats the other CRF systems and all. So this is, I should point out, this is not supervised CRF. This is unsupervised CRF. Supervised CRF probably will have better things, will have more labeled data. So it may perform better. Yeah.
How large are those test sets?
Sorry?
How large are the test sets?
Yes. Do I have in this? Oh, no, I do not have in this. I'll cut back to this problem. So over here, I think we labeled around 500 posts with symptoms and drugs and treatments. And each post will have probably 10 to 15 sentences. So in summary, we saw that Bootstrap Pattern Learning was pretty effective at learning new entities and morphological variations of the existing ones. And we beat all the widely used medical entity extraction systems. So the two applications suggest that Bootstrap Pattern Learning is pretty effective, and all you have to do is provide some seed sets. The next part of the talk is how to improve these systems. So I talked about the two most important components in this architecture is improving the patterns and improving the entity scoring. And the first part, I talk about how to improve the candidate pattern scoring. So if we step back and think about these kinds of bootstrapped systems, what happens is we have a few positive examples, a few negative examples, and large unlabeled examples. And what people do usually in previous past work is they make closed world assumptions about them. So what I mean is either they assume this data to be negative, they ignore them, or they do some combination of both. So for example, if they're assuming that they're both negative, so all the unlabeled entities are negative. If you remember, our patterns owner X, my pet X, they were both extracting one positive and one unlabeled entity. In which case, if you're assuming the unlabeled entity to be negative, both of them would be negative. So you would score both patterns as same. But this is too conservative, because my pet X is actually extracting a good unlabeled entity, but we're not doing anything about it. Similarly, if you just ignore them, then it does not differentiate between good versus bad unlabeled entities. And again, both of them will extract only one positive entity, so like give them the same scores. Or you do both. So what we do is that we predict labels of unlabeled entities using unsupervised measures. So we don't want to put in any more supervision than we have to start with. So coming back to the example over here, each pattern extracted dog and one unlabeled entity, and we have some scoring system, S1 and S2. If we had labeled data, we would have known that house is negative, cat is positive. We would have scored my pet X better than owner X. But we don't have any such labeled data to give us this. But what we do have is similarity measures, unsupervised ones, that tells us that cat and dog are probably more similar than house and dog. And we can predict the labels of these unlabeled entities. So we can have some notion of maybe house is 0.8 negative and cat is 0.1 negative, and include that when we are scoring patterns. So we exploit the unsupervised scorings. So over here, this is the new pattern scoring function, and the contribution is the word expected. So you say that over here, I'm going to calculate the number of negative entities extracted by a pattern. So this function scores one pattern at a time. And for each unlabeled entity, I'm going to score that unlabeled entity, that how much is it negative. And
quick question.
Yeah.
So this pattern, this scoring function is asymmetric in the sense that you could have done the expected number of the positives as well, but why are you only doing the expected number of negatives?
If you have, right, there wasn't a big design decision in that. It could have been the other way around too. So our focus was specialized domains because we were dealing with this MedHelp data set, which was more focused on specialized domains. So something like in biology, medicine, law, we have very little coverage in Wikipedia, WordNet, or Freebase to derive any of these similarity scores. There's no web scale data, so there's harder to get list wrappers and so on. But we defined 5 unsupervised weak predictors, and in this paper, at least, we averaged their scores, but in later papers, we have a classifier that can combine these scores. But averaging also works pretty well. So the score is between 0 and 1, and this is just average of the features I described next. So in a lot of web data, you have misspellings or variations of already known entities. For example, penicillin and penicillin are pretty close by, so you can just look at the edit distance from the positive entities. You can look at the edit distance from the negative entities. So these are the 2 edit distance-based features. Very simple ones, but they work very well with web data. And especially if you have specialized domains, you can see how common is this word. For example, if you have the word YouTube, it's probably not a drug or a treatment. So you can have some Google Ngram TF IDF approach. And then you want to see in word vector spaces, how close is this entity to the known entities? So you have clusters of words, and you label each cluster, is this a positive cluster, is this a negative cluster, based on the entities on that cluster. And this turned out to be a very powerful feature. And another one which we had, because we have multi-word phrases, is just to see how often does that word occur in positive versus negative phrases. So John is more likely to be a name and then a place, because it might occur in name phrases. So you just look at the ratio of frequency of the phrase in positive versus negative. And our experiment was similar, in which we are extracting drugs and treatments and from the similar kind of text. And we are measuring precision and recall. So precision is just the same as usual. So you extract percentage correct among extracted. And the recall is a bit different. We do not have any fully labeled data set, and they're pretty huge data set. So what we do is what other people have done in the similar case scenarios. You run all the systems, you get all the extractions, and then you pool all the extractions together. You label each of the extractions whether this is good or bad, and then measure recall in this pooled output of the systems. And you stop learning each system if the precision drops below 75%, because then otherwise you're extracting too many noisy entities, which are not that useful. So here is for acne, around 65,000 sentences. On the top is our system in black line, and these are all the other baselines that we compare to. And our system performs better almost all the time. So on the y-axis, we have the precision. The x-axis, we have the recall. This is for diabetes. All the systems perform pretty badly on it. And the reason is that it has a lot of home remedies. And
food items that are not found in any of the seed sets, like quinoa, yoga, and stuff. But still, our system beats other systems. This is on asthma. We again perform better than the other baselines. ENT. So we talked about the Bootstrap pattern learning system and how we can improve the pattern scoring measure by evaluating the unlabeled entities. And next, we'll talk about how to improve the entity scoring measure in that. So in this flowchart, we are now improving this component of the system. So for entity classifiers, the training data is, what positive is the seed and the learned entities of the type, and the negative data is entities of the other types, and randomly sampled unlabeled entities. So this data set is pretty limited and noisy. The reason it is limited is because we have very small seed sets. And the reason it is noisy is because these randomly sampled unlabeled entities, they can be positive, but we are just sampling them as negative, which is a huge problem in any of these bootstrap systems, that you sample the unlabeled as negative, but you have no idea what the label actually is. So question is, can we improve creating this training data set? And more specifically, can we expand the positive and negative training examples and make it better? So our solution is we find entities similar to the known positive and negative entities and add them to a training set. So, and the way we do that is use these word embeddings from deep learning literature, and they have been shown to be really good at capturing the semantic and the syntactic similarities. So for example, over here, this is plotted in 2 dimensions, and each word over here is a vector. And this shows that it gets some of the syntactic ones on the semantic meaning. So on the left are all the countries, on the right are all the capitals, and they basically get clustered together that way. So these word embeddings are pretty powerful. So we use these word embeddings and the unsupervised learning of syntactic and semantic similarities to aid the generalization in our system. And we expand the training set by looking at the k nearest neighbors of the seed entities in this space and adding them to the set. Pretty straightforward, simple approach, but actually works. So for example, if this is our training set, on the left are the 2 positive examples, and we are learning drugs and treatments. So vegetables might be a drug and treatment for diabetes, and ibuprofen is a drug and treatment. And you have some negative examples like feeling nausea, doctor, and man. And you expand the training set. So you will expand quinoa, yoga, which actually got expanded. We added quinoa and yoga in the data sets. Sanitizers, omegas, and so on. So you improve the training, you're improving the training set, and thereby improving the entity classifiers.
So there's something recursive here. You're kind of finding extra positive examples to help you find extra positive examples with your patterns. Right. So you've kind of got 2 separate learning systems. One's expanding the training, and then your patterns are then expanding the data sets further. So it seems like there's a balancing act you've got going on. You know, how much do you expand the training set initially versus how much do you let your pattern learner expand it? Right. How do you manage that balance?
Right. So I would say that expanding the training set is less of a worry than the second one. The second one actually does all the learning. So you want that one to be much more accurate than just expanding the training sets. And because training sets, it is a classifier, it can handle some robustness. It has inbuilt robustness. You have features to do it. So that you can expand this generously. You can do things with it generously because it's a classifier. It has some robustness built in. But in the second one, it's not. You have to be a bit more careful in what you're learning, how much you're learning in each step, and so on. Yeah, it is a delicate balance. And the key idea over here is that you use the similarity to label the things, training sets indirectly. So this answers your question of, we are not labeling it directly. We are not labeling the data just using this similarity measure. And we show in the paper it actually leads to a lot of noisy labelings if we just use the similarity measure to label new things. We are using it just to build the training set, which handles some of the noisiness. A few results, for example, acne. The top on the red is our system in which we extract the training set. On the black one is when we don't expand the training set, and the average one is when we just average the features, don't use the classifier. Diabetes is again a very hard data set, but our thing still performs better. ENT, asthma. So in summary, bootstrapped systems have limited and noisy training data sets, but we can improve those training data sets by expanding the current one using unsupervised similarity measures, and distributed representations of words are pretty good similarity measure to do that. So I have the SPIDE, which we call Stanford Pattern-Based Information Extraction and Diagnostics, available as part of Stanford Core NLP, so you can download the system and run on your data set. Here, I just wanted to give you a peek into the GUI I developed. Initially, it was just for me to do diagnosis of what's happening in the system, where the errors are coming in. But I'll go into each of them. What over here are, you can compare two systems. So on the left side is one system, on the right side is one system. And you can see how they're performing depending on what parameters you have changed. So what are the new errors that have crept in and why they have crept in, or what things you're doing better now than before. So if you zoom into one of those entities, over here, promise is one entity that got extracted. And we are learning, this is an example use case, and we are learning the names of presidents. And so you say that promise is a wrong entity that got extracted as a precedent. And the reason it got extracted is because this pattern extracted it, which is basically something which is a name followed by this target entity. Obviously, it's a very bad pattern. You can just look at it and see that does not extract any precedent whatsoever. And you can look at why this pattern got extracted, because these are the positive, negative, and unlabeled entities it is extracting, and how good these entities are. And then maybe get an intuition of how do you improve the system. That maybe I need to look at more things on the left, not just one token on the left, or more things on the right, and so on. You can have a pattern-specific view in which you can look at one pattern and not an entity and see what it is extracting over time. So over here you can see that this is a bad pattern. Someone pledges, doesn't mean that the president is pledging, right? And it extracts like campaign is pledging something. This is unlabeled entity extracts, which is a wrong entity. So it gives you an intuition and diagnostics, some interpretability to improve the system. I just wanted to talk about, for 2 minutes, of other work I've done, which I have not talked about in this talk, but I would be happy to talk about later on. So this is work in collaboration with Interactive Data Lab at Stanford and UW. So Jeff here, who was at Stanford, now moved to UW, and his students. So in the first project, I worked with Diana McLean to analyze the online addiction forums. So why people are on the addiction forums, what are they posting, what are they addicted to, is the forum helping them get better over time or not, and what are the things that are helping them. In the second one, which I think someone told me people are also working over here, which I would be very interested to know, is this manual and automated text annotations frameworks, in which we are doing user studies to see what frameworks are better for people to annotate sequence labeling tasks, and maybe have an automated system on the back that gives you suggestions. Do you want to annotate this entity as name, for example, which would be then the SPIDE system at the back. And brief work with evaluation of topic models with Jason Chuang, who I believe was here. So things that I have not talked about is amount and quality of supervision, which is a very open-ended problem and pretty interesting one. How much supervision you need and what quality of it. How do you avoid semantic drift from happening? One thing I'm actively working on is patterns as features and sequence models. So these patterns are basically really good features. And I believe this pattern learning is a really good feature selection technique, in which it learns these contexts, these feature templates over time, and see these are the good ones. And if you include that as features and sequence models, how much better are you getting? Better ways to conceptualize and generate these patterns. So right now, we have only one weight for each pattern. But you can imagine weights on parts of pattern and a way to combine them together. But also then there's a trade-off between interpretability and complexity of pattern. And maybe a human study is required. How much complexity can humans really take in understanding something? And application of this to many different things, like so we can sequence-based tasks, and knowledge graph things, relation extraction, and so on. So in conclusion, many real-world applications of information extraction, they have no labeled data. Someone wants to extract some very particular information from some data set, and they do not want to label data. And we saw that Bootstrap Pattern Learning is an effective approach to do it. And it learns these really good feature templates with using very little supervision. And these patterns are understandable to humans, and they can use it to cope with errors in a real-world deployment. And in any kind of Bootstrap systems, if you have unlabeled data, then we really need to evaluate the unlabeled data to make the classifiers better. Thank you.